Here we have a great problem. We have the integral from 0 to 1 of sine of t squared dt. Our instructions here are to use a calculator or computer to find the value of a definite integral. So this is just say, hey, let's use our calculator to find this integral. So we go math 9. We want sine of x squared with respect to x from 0 to 1. We can just plug it into our calculator. Before we hit enter, we're going to go and switch to radian mode because I just remembered that I did just do a trig class, so we're in degrees. Now that we're back into radians, we just hit enter and we get this value. We weren't worried about anything like the area, so we didn't have to worry about above or below the x-axis. Just make your calculator crunch some numbers, and then you get 0.31, how many did it want? 4 decimal places, 303.3103. So we just need to know our calculator syntax for this, which is fn int is the command, and it opens parentheses. The first thing we put in there is the function sine of x squared, close parentheses, comma, with respect to x, that's us saying the dx part of the integral, from 0 to 1. And then we just have to remember that fnint is the math button. Usually when I make buttons, I put it in a box like it's a little button. And then when we hit the math button, it's in that first, it's in that first column of commands, it's number 9. So if we just press 9, we'll bring up the fnint. So math, and then in the math menu, it's 9, fnint, parentheses. So we can just press the math button, then 9, and that'll bring this command to the front, to the home screen. Any questions? Here's the other reason that I like this problem, because like we had in the previous problem, that is secret math knowledge, we also have secret math knowledge for this one, which would be the fundamental theorem of calculus, where we find the antiderivative of the function and then plug in the endpoints. But they're kind of anticipating that we might have secret math knowledge in this problem by asking us to integrate sine of t squared, because we don't know what the antiderivative of sine of t squared is. So this was a clever move on whoever wrote this book, saying, oh, we're going to force you, or wrote this problem, we're going to force you to use a computer for this or some other approximation method because we don't know the antiderivative of sine of t squared. So even though we have secret math knowledge, we don't know this particular antiderivative. So that's thwarting our ability to use the fundamental theorem of calculus by finding an antiderivative and plugging in the endpoints. Most likely you wanted to just plug it into your calculator anyway, because that's what the instructions said. Any questions? Another thing you can do is look at a graph of sine of x squared. Look at a graph of sine of x squared, and then integrate from 0 to 1 from the graph. So second, calculate, integral, starting off at 0 and ending at 1. It'll shade it in for you, and then we'll know that this is how much the antiderivative is changing from 0 to 1, because there's no, the area is all above the x-axis. Another interesting thing to note is that what we're doing when we make sine of t squared instead of just sine of t squared is, what's happening is t squared is compressing the x-axis down. That's why it looks like the sine is getting squished in. Because instead of just running through x in a nice regular pattern, we're running through x at the rate of x squared instead. So that's why we're seeing this compression. Infinity is coming faster because we're not counting 1, 2, 3, 4. We're counting 1, 4, 9, 16, 25, and so on. So we want to think about doing sine of t squared. This is changing the way we're counting, and that's why it looks like the period is getting compressed as t increases. So DVD bonus material from pre-calc, depending on how deep your pre-calc went. Any questions? Rad. Let's pause the video here and move on to another problem.